to this first session, the very last day of DPVSA 2021. I'm Bruno Zatti. I'm professor at the Federal University of Pelotas and one of the researchers of the Video Technology Research Group. So good morning, good afternoon, good night. Today is my pleasure to chair this session with Caroline Conti. So welcome, Caroline. She is a professor with the Department of Information Science and Technology at the Instituto Universitário de Lisboa and senior researcher at the Instituto de Telecomunicações in Lisbon, Portugal. She got her BS degree from the Universidade de São Paulo in 2010 and her PhD from the Instituto Universitário de Lisboa in 2017, so very recently. And her interests in terms of research include immersive visual technologies, image and video processing, including, of course, light field processing and coding. She has contributed to many papers and in these areas, and also participated in many research projects, both in national and international, jointly with academia and also industry. She is currently guest editor of the Elsevier Signal Processing Image Communication Journal for the special issue on light field imaging, and is topic editor of the MDPI Journal of Imaging. She has been a member of organizing committees of many international conferences and acts as reviewer for many IEEE, ERASIP, and MDPI journal and conferences. She has also been recognized with many awards and distinctions from national and international conferences and competitions. And more significantly, in 2016, she won the 27th edition of the Portuguese IBM Scientific Award, an award for outstanding technical contribution in computer science and related fields, considering her contributions to efficient solutions for light field coding. And of course, this is the topic she's going to bring to us today. The title of her talk is Light Field Processing, Challenge and Solutions, a topic that's very dear to me. And of course, it's a hot topic in terms of visual signal processing. So Caroline, be very welcome. The floor is yours, and please enjoy your talk to us at the very end. I'm sure I'm going to bring many questions to you.
Okay, good morning, bom dia, good afternoon, good evening. I'm going to share my presentation here. Just some minutes. As Bruno said, I'm Caroline. I'm Brazilian, but I've never been to the south part of Brazil. I hope next time I'll be able to go to Brazil to be with you all. And I came to Portugal in 2010, just to contextualize. I came to Portugal in 2010 to work in an European project called the 3D Vivent. And it was a quite big project, and it was related to light fields. Many countries were involved. And the goal was to develop a system for immersive medias focused on light fields from capture to display. And Portugal was responsible for developing the coding part. That's why I started working on light field coding, and I've been working since then on light field coding and processing. That's why I bring today this presentation, light field processing, some challenges and solutions. My intention with this talk is not to bring any specific, to focus on any specific solution, technical solution, but to provide you an overview about immersive media, light fields, the pipeline, possible pipeline for light field processing, and to talk about some light field representations in the context of coding and rendering, and some current trends on light field processing. Okay. And when we talk about light fields, we are talking about immersive media. And from where comes the need for immersive media? And we know that comes from the dream to have the same feeling we have when we interact with the real world. For instance, when we see a landscape, we want to see all the details about the lighting, about the reflection on the water. We want to see the changes on the reflections when we move around the scene. We want to move freely on the scene. And I like to show this picture just to say that we are getting there, but we are not quite there yet. Because first, we still rely on glasses, and these glasses, these headsets are not natural. And second, the images that are used to feed these displays are still distorted versions of the reality. And how can we get there? If we are talking about visual capture, we have to capture more information, and we try to improve this degree of immersion, improving the spatial resolution. We are talking about the spatial dimension. We go from LCD to nowadays 8K resolution. We can talk about the temporal resolution. We want to improve by increasing the frame rate when we are capturing the content. If we go to the color dimension, we talk about going from standard dynamic range to high dynamic range. And of course, if we are talking about immersion, we also talk about the angular dimension. And in this case, we want to improve the sense of depth, and also we want to improve the mobility of the user. We want the user to see different perspectives as he moves around the scene. And then nowadays, when we are talking about immersive media, we are mainly focused on this dimension, the angular dimension. Of course, not forgetting the other ones, but mainly focus on the angular dimension. If we go to the other side, if we talk about visual graphics, computer graphics, we see that the recipe was the same. Since the first games that we saw in the marketing to the games we see today, the images, the recipe was the same. We try to improve the graphical details, to improve the color resolution, the depth cues, the realism of the movement, the animation, the details in lighting and material, and also improve the hardware with accelerated graphics for rendering this kind of content. And we see that we have two words, one for capturing content and the other for generating content. And we can say that light fields start merging these two words in the 90s when they start to think about, is it possible to capture real objects and then take advantage of these advances in computer graphics to render new views? And they started talking about this in the 90s, and a milestone in this thinking is a paper of Adelson and Berger in 1991, where they try to talk about how can we parameterize any imaging system from our eyes to any system of cameras in order to represent the visible light as accurately as possible. And they said that for this, we need a 7-dimensional function, the so-called planoptic function. And in this case, we are trying to describe light, a light that propagates in the 3D space. And then we have the parameters X, Y, and Zeta for the position of a light ray in space. And this light propagates in a specific direction given by the theta and phi dimensions, and this light has a wavelength, lambda, and propagates through time. Then we have the t dimension for time. And we have a 7-dimension to represent this light as accurately as possible. But of course, we can do some simplifications, and some common assumptions. The first one is, if we consider that the light is propagating in free space, we can then discard the zeta dimension, because we consider that the radiance is constant along this dimension. And then we can have a 6D planoptic function. Another common assumption is that since our human vision system is more sensible to the colors red, green, and blue, we can split this planoptic function into three, one for each channel. And then we come up with a 5D planoptic function because we discard the lambda. And then, of course, if we are talking about images, we don't have the time dimension. And then we come up with a 4D planoptic function where we have 2 dimensions for space and 2 dimensions for angular. And this for the planoptic function that is known as the light fields. Of course, we can have light field videos. In this case, we have the 5-dimensional planoptic function. We are now in the 90s, and we can think this is not the first time they were trying to describe light. And we can go a little back in time, and 60 years before, in 1936, and we can see the work of Andrew Gerson. And this was the first time the term light field was introduced. And he said that light fields is the light beams that propagate in a straight line through a 3D medium, a homogeneous medium, a 3D space, okay? We are in 36, but if we go back in time a little bit more, we are now in 1908. We see the work of Gabriel Lippmann. Gabriel Lippmann was the supervisor of Marie Curie. He was also a Nobel Prize winner, and he introduced the concept of integral photography. He envisioned a system for capturing the light field. And this system was envisioned thinking about the fly's eyes, where we can see many micro lenses in the fly's eyes. And he called this system integral photography to capture the light field. Of course, we can go further and further through time, and we can see works of many people discussing how to describe light. And we can go even more to the 15th, 16th century, to the journals of Leonardo da Vinci, and we can see that he already tried to describe light, and he says that light rays propagate in radial pyramids. He was trying to understand back then, and he even envisioned a device for capturing every optical aspect of the light. This is just to say that the concept of light fields is not new, but only today, only with the advances in optics, sensors, and hardware and software, only now we are able to capture the light field. And when we are talking about light field imaging, how to capture, the idea is to capture all the light information in a 3D space. And we can think, if we want to capture all the light rays, we can use infinite number of cameras to capture all the possible perspectives. But of course, if we consider this, we can see that, for instance, this camera is capturing the same ray as this camera back there. There is redundancy. Then maybe we don't need infinite number of cameras. We can have a sample of this light field, for instance, using a wall of cameras. And if we can capture all this light information, we can follow an approach, capture everything, and compute later. We have all the light information, we can compute, and we can do rendering after the fact. And with all this light information, what can we do? We can, for instance, construct the 3D model of the object. In this case, the 3D model was captured with a wall of cameras, but if we have more cameras, we can reconstruct the entire object. Also, when we are talking about rendering, if we have all the different perspectives, we can use these different perspectives for render new views, and then we can change the perspective to render new perspectives of the scene. And we can also have rendering with flexible capabilities. For instance, we can change the plane of focus. We can do refocusing after the fact, not after we capture all the light information. We can also change the depth of field, which means how many planes are in focus at the same time. And also do some effects that are not natural to us. Some effects like the dolly zoom, where we go back, the effect is like when we are going backwards with the camera, at the same time we are zooming in an object, and we can have these effects that are not natural to us. We have flexibility in rendering using the extra light information. And this flexibility can be used in some applications, for instance, in cinematography. In cinematography, what we have a director that wants to tell a story, and sometimes he uses the focusing to capture the attention of the viewer. And for doing this, usually there is a guy that's called the focus puller. This guy is in each instance of the scene, when the scene is being captured, he's changing the focus. And if he does something wrong, the director will say, okay, we have to shoot again all the scene. And if we have a light field system capturing this, we can do refocusing after the fact. We don't need to reshoot all the scene. Another example in cinematography, we can use this extra light information to take the depth map of the scene, and then we can do composition, and then we can replace the called chroma keying. We don't need this green screen to do composition. We can use the depth map to take the foreground object and then to change the background and compose the scene. Another area of that can take advantage of this is entertainment and gaming. In this case, we are talking about mixed reality, augmented virtual reality, and all in between. And in this case, if we have the 3D model of the scene, the capture real scene, we can construct this 3D model, and we can allow the user to visualize with all the 6 degrees of freedom. The user can see the scene, can rotate his head to the left and right, tile up and down and out to the left and right, and also navigate in the scene, go forward, backward, to the sides and up and down, all the 6 degrees of freedom. Another thing that's possible, we can blend a 3D model of the real object with a 3D model of synthetic content. And this blend can be seamless using this type of technology. And this example that we can see at the right is from a demonstration that Google did last year. It's called DPVSA video, where they captured light field video. And we can see here an example using a virtual reality headset. And what we can get in when we are using virtual reality with this type of content. If you look at the display outside here, we can see the reflection of the light. There is a light bulb here. We can see the reflection, and when they move to the left and right, we can see that these details of the reflection changes as we move. We are not anymore seeing that distorted version of the reality. We can have all these details in the scene if we capture the light field. Also for entertainment, we can consider light fields for content visualization. In this case, we are considering the called light field displays. In these displays, we don't need to have glasses to have the sense of depth, and we can have the mobility. The user can move around the scene and see different perspectives. There are 2 types of displays. One display is called the autostereoscopic, and in this case, there are many lenses that's showing slices of different perspectives. That's why we have the sense of depth. And the second one at the right is a display that was demonstrated last week. It's called the solid light display, developed by the Light Field Lab. In this case, they have many projected cells projecting light in different directions through a special screen that split these rays, and by the intersection of these rays, the 3D object is reconstructed in front of the display. Then we see really the rays being reconstructed in the air. It's very impressive. And there is also a company in Hungary that has been producing this kind of displays for a long time. And I had the opportunity to do an internship. It's called Holográfica. And they have a setup for cinema. And it's very impressive to see the type of images that we can go around and see different perspectives. It's very impressive. If we have this type of applications, we can also apply for medical imaging. And in medical imaging, what can we do? We can visualize the content. For instance, we can have the doctors wearing AR glasses and visualizing an object in front of them, and then they can control this object by voice, and then don't need to touch on anything. They only touch on the person, and they can control everything by voice. Or we can use also for create content. In this case, there are an example of a an European project. There is a Portuguese laboratory working on this also. That's called the volumetric medical X-ray imaging at extremely low dose. What is the idea here? Here they are not capturing visible light, they're capturing X-ray light, and they are trying to reduce the X-ray irradiation on computed tomography using light field capturing. That's the idea in this kind of projects. Just to show that light fields can be applied to visible and also any other light, including X-ray. If we have many applications that we can, prospective applications, let's think about some possible pipelines for light field processing that will allow this type of applications. And I put here one possible pipeline. Of course, this is not fixed for all applications, but that can work, for instance, for entertainment. And what would we have in terms of processing? Of course, this pipeline begins with production. We will create light field content, or we will capture light field content, and then post-production, distribution, and then display. I put many boxes here about what we can do in terms of processing in this pipeline, but let's discuss first the production, what we have in the production side, and what is expected to display to understand what we have in between, okay? Let's start here with the production. And here we can, as I said, we can capture the light field. I will focus on the capturing, but we can also create and estimate, blend with the geometry information and have a hybrid content. But let's look at the capture. How can we capture light fields? And as I said, we can capture using a wall of cameras. In this case, is the camera array. We have many cameras capturing, each camera captures a different perspective of the scene. And what we have a 2D array of 2D views, each camera capturing a different perspective. And these cameras can be close together or can be far away of each other. We can change the setup of these cameras to capture many views. Another approach, instead of using a wall of cameras, we can use these cameras on a sphere. And we have two examples here. One is the Otoy setup, where the cameras are pointing towards the center of the sphere. And the other one is the Google Deep View they used last year, they proposed last year, to put the cameras as in a concave surface. And convex surface, sorry. And what we have in this case, we have multiple views again, multiple different perspectives of the scene. Just to show you that we are already using this. This Otoy setup here was used in the last Avenger movies to capture the face of the actor, the Ruffalo. They took many pictures from him, all the details of the faces. They used these pictures to construct a 3D model with all the details of his faces, and then to fasten the construction of the Incredible Hulk. the 3D model of the Incredible Hulk. Okay, they are already using this type of things for producing films. Instead of using a camera array, we can replace the camera array also by camera rigs. In this case, we can have only one camera capturing different images through time. If this camera, and then this camera can move in all 6 degrees of freedom and capture different images of the 3D space. Another setup that's possible is using this camera rig that was proposed also by Google in 2019. In this case, they use many GoPro cameras here, and they capture thousands and thousands of images. In this case, we also have multiple views of the same. Another approach is, instead of using cameras, we can use a planoptic camera. Regular cameras we replace by planoptic cameras. And then what do we have? Instead of having many perspectives, one from each camera, we replace this by a micro lens array. And this micro lens is put inside only one camera. And then each micro lens will capture a small different perspective of the scene. And we can see that the image that's captured in the sensor is formed by a 2D array of 2D micro images. And this image is called lenslet image. And we can have many different micro lenses. This micro lens can be rectangular, hexagonal grid, or we can even have different micro lenses in the array, micro lens with different focus length. And of course, we can use different optical setups, and then we can have cameras that will produce different type of images. The planoptic camera 1.0 and 2.0, for instance. The difference between them, we'll see how we will do, how we will do the rendering in these cases. Just some examples about the planoptic cameras. We have, we saw some planoptic cameras in the market. We still have planoptic cameras in the market. The most popular one was the Lytro. Lytro launched many cameras, the Lytro first generation, Lytro Elum, around 2010. And also a very huge camera, Lytro Cinema, with a huge sensor. But now they are not producing anymore. The company has closed. And most of the people that were working on Lytro now are working on development on Google. And also the CTO of Lytro, the person that was CTO at Lytro now is the CEO of the Lightfield Lab, and they are now producing displays for light fields. But we also have this Raytrix. Raytrix is a German company that are still producing planoptic cameras. And these planoptic cameras there are many different planoptic cameras, even for microscopy. And they are available in the market nowadays. We saw how to capture light fields. Now let's see how can we consume light fields. And for consuming light fields nowadays, we have to consider all the different technologies for display. And we have to have different displayable versions of this light field content. We can consider that the user can see this content from a 2D display, from a smartphone, from 3D stereo TV, VR and AR headsets, and also alternatively using a light field display as the looking glass and the solid light display. We have many ways to consume the light field. Now that we saw how to capture, how to display, we can also talk about the challenges that we will have. And the first one that is the most obvious one is that we have to deal a very huge amount of data. There are many views that are captured. We have to deal with this huge amount of data to be processed, distributed, and displayed. And just to put on some perspective, I put here the example of the Lytro Cinema camera. I said that this camera used a huge sensor. The sensor was 755 megapixels, and they capture video with 300 frames per second and with 16 bits per samples. If we do the calculation, this means that to record this content, we will have to record 3.6 terabits per second. This means, I just look at the internet, if we have to record this content on hard drives, and I look, what is the fastest hard drive that's easy to buy? And I saw the fastest hard drive can write with 6 gigabytes per second. And imagine we have, just to be easy to do the calculations, hard drives with 1 terabyte of capacity. In this case, for this camera, we would need 71 hard drives of 1 terabyte to record these 3.6 terabytes per second in parallel. And this just to record 2.9 minutes of video. Then imagine how much information we have to deal when we are talking about light fields. And this was one of the reasons why Lytro Cinema is not in the market nowadays. I like to think that it was too ahead of the time. Another difficult challenge that we saw that there are many ways to capture the light field. And the different systems will have different spatial resolution, angular density, field of view, and cost. And we can see an example here. If we are considering an array of cameras, we can consider the distance between the cameras. If we change the distance between the cameras, if we are putting the cameras further away, we are able to capture sparser light fields. If we instead put the cameras closer together, we are able to capture denser light fields. With the distance between the cameras, we can control the angular density. And also with the distance between the cameras, we can control the overlapping field of view here. If we are talking about the sparse, this overlapping is smaller, and then rendering will be a bit more difficult. If we put close together dense light fields, we will have this overlapping fog larger. And when we are talking about dense, we can think that if we put so close together all the cameras, we go to the micro lens based approach, the planoptic camera. And in this case, we have the densest light field capturing. We have many different ways of capturing, and all these resolutions will be different. To the display side, what we have to consider, if we are talking about different display technologies, these display technologies and also the applications interaction capabilities will determine what the user needs in terms of spatial resolution, angular density. We can say these two together, we can say that is the ray density of the display. The field of view also, what is the degree in which the user can have this depth feeling, this depth sense. The interactivity, the level of interactivity will change also when we are talking about virtual reality displays compared to 2D displays. The level of interaction is different. And also the viewport mobility is different. Some application needs only 3 degrees of freedom. Other applications will need all the 6 degrees of freedom. Another important aspect here is the latency. Some applications need very low complexity, and we have to consider this when we are talking about coding and rendering. Just to give some examples, I put here some of the displays that we can see nowadays. 2 of them for mixed reality, 2 of them light field displays with no glasses. And we can see that for all of them, the field of view needed for the display changes. For the Oculus, we have 110 degrees for field of view. For the Magic Leap, we just need 40 degrees for FOV. And when we talk about the 2 light field displays, we have 50 degrees for the looking glass and 100 degrees of freedom for the solid light. Also for the ray density, if we talk about the looking glass display that was launched in 2020, we are talking about a sensor of 8K ray density resolution. 1 year later, if we talk about the solid light, what do we need to have this kind of displays? And they talk about 10 billion pixels per meter square resolution, ray density. And we can have an idea how much data we have to capture or render for this type of displays. Since we saw some of the challenges for the pipeline, for the light field pipeline, we see now, we can see now what do we need in between the production to the display. We saw that there are many ways to capture the light field, and all of them have in common the huge amount of the data. And then an important requirement for coding here, when we are talking about distribution for coding, is compression efficiency. And we saw, since we have many ways to capture, we can represent in different ways this light field content. That's why we may need an intermediate representation for processing here, this content. That's why here in post-production, we may have this block here to define which representation we are going to use to represent the light field, the different capture light fields. Another important requirement, when we are talking about, for instance, VR, we may not need all the light field information at once. We may need only the perspective that the user is seeing. And in this case, we need to have this feedback here between display and distribution. And we need to allow somehow random access to these views. And this has to be considered when we are talking about coding and streaming. Another important requirement is that since we are talking about different display technologies, it will be advantageous to have at the bitstream level some kind of display type of scalability, to have sub-versions of the sub-bit streams for different display technologies. And in this case, we are talking about scalability in terms of spatial resolution, angular resolution, and quality. And of course, another important requirement is about latency. As I said, some applications, latency is very important. And also when we are talking about the different users, seeing the content, consuming the content on the internet, the bandwidth of the user, we will also define the latency, and we have to have a low complex coding, low complex to allow to interact with this content, even in limited bandwidth. And another aspect that's very important, how can we access the quality of experiencing? If we are considering that we have many different technologies for consuming at the display side, we have to consider how to access this this technology differently for each display. We have to consider that the light field will be consumed by different displays. These are some of the important requirements that comes from the challenges in this pipeline. Just to summarize here, we go from the production, where we can capture the light field, to the post-production, that maybe we will need an intermediate representation, and this representation may need more information than the one that was captured. That's why we may need to reconstruct some of the information. We can also estimate the geometry from the captured light field to improve this representation. Then we can go to coding. We need coding efficiency here when we are talking about coding and streaming. And we know that at the display side, we will need to render content to the different display technologies. That's why we have this render block, and this render can be done at the display or can be done in the cloud. And the different display may need a different spatial resolution, angular resolution. That's why here at the display, we will need also somehow to improve, if we needed to improve the resolution, to use super resolution at the display. And we also need to allow the user to interact with this content. That's why we need to consider this interaction. And also at editing, we can consider, for instance, the user can be seeing the 3D model, and the user can also include some other objects on the scene. That's why we need also to consider editing here. This is just an example for the light field pipeline. As I said, it's not fixed. It's just to give you an idea, what do we have to do with this kind of content since production to the display? And what are the challenges when we are talking about light field processing? Now that we saw the processing pipelines, let's talk a little bit about, let's focus on the representation and to talk a little bit about what are the possible intermediate representations for light fields. And I'm going not to focus on specific representations, but I will give you an overview. And I will talk about the pros and cons of some of them in terms of coding and rendering. And since we are talking about representation, we have to consider what we have from the production. What is the production representation when we capture the light field content? And in this case, we saw that if we are using a planoptic camera, we have as the production representation a lenslet image. This is called the lenslet format. In this case, we have the 4D because we have the 2D array of 2D microimages. And if we capture this content with a camera array or a camera rig, we have the content at the production is a 4D multi-view format because we have a 2D array of 2D views. And we can convert from one to other, okay? These are the two production representations. But when we go to the literature and we talk about how to represent the light field, we can see that there are many alternatives to represent the light field information, and we can categorize them between texture-based, or as some people in the literature say, pixel-based, the kernel-based, and the voxel-based representation. The voxel-based is the representation based on point clouds or meshes. The kernel-based, instead of using the pixel or the voxel representation, they use a kernel-based representation. And one example of this is this stir mix mixture of experts, where they use a Gaussian mixture model to represent the image. And I'm going to focus here. I'm not going to talk about point clouds, light fields, and kernel-based. I'm going to focus here on texture-based representation. And in this case, we can consider only the texture information. And here we have the two production representations, the lenslet and the 4D multiview. Or we can organize these representations in different ways. And then we have representations like the pseudo video sequencing, a 4D volume, a 4D superpixel. If we talk about texture and we want to improve a little bit more this representation with more information, such as the geometry, we can estimate the geometry from the light field, and then we can have other types of representations, such as the multiview plus depth map, multiview plus a graph representation of the geometry, focal stack, Fourier disparity layers. And then we can even improve a little bit further, and we can have the geometry and also other information that can be important for rendering, such as the information about the materials, the transparency, the opacity, and also information about the occlusion of the objects. Then we can have we can estimate this information also, the transparency map and the occlusion map. And then we are talking about representations such as the multiplane imaging and the multisphere imaging. I'm going to talk about some of these representations, and then I'm going to discuss some pros and cons for each of them in terms of coding and rendering. Since we are talking about coding, then what you have to remember from the previous days, you have opportunity to see many presentation in the previous days talking about image and video coding. And here I'm going to focus on image and video coding standards. How can we use the image and video coding standards for coding light fields? And you saw in the previous days that there are two committees that publish image and video coding standards, the JPEG and the MPEG for image and for video. And they've been working on this for more than 30 years. There are many standards available, but I'm going to focus on the standards that allow high compression efficiency for high resolution images. Then I'm going to focus on, for instance, HVC, VVC, and the extensions of HVC for multiview, 3D view, 3D coding, and the screen content coding. And of course, since JPEG and MPEG started the standardization activity also for immersive media, I'm going to consider these two standards, the JPEG Plano and MPEG-I. And the JPEG Plano already has published a standard this year for light field coding. But the two activities are working not only on light field coding, but on the standards for other imaging modalities such as point clouds and holography. And MPEG-I published this year the standard for point cloud coding. Then I'm going to focus on these standards and how can we code the light fields using these standards and using the representations that I will talk about. I'm going to jump to conclusions in the next slides, but if you want to see some more details, you can see in this paper that we published last year, where we do a comprehensive overview on light field coding, and we talk about alternatives for light field coding and many other approaches, okay? I will just do some examples and jump to the conclusions, okay? So let's start with the lenslet representation. Since we have this is the simplest representation, how to represent the light field as a 2D image. In this case, we have a 2D array of micro images. And since we have a 2D image, we could code this image using a 2D coding solution, such as HVC, or VVC, or AV1, any solution for 2D. But if we look at the images, we can see that this lenslet image has many micro images that are very similar to each other. Then we could use another standard that try to take advantage, to create a better prediction, to compensate this non-local spatial redundancy here. And there is a standard codec that do this, that is the HVC screen content coding. Then we could use, to achieve high compression efficiency, we could use this standard to compress this lenslet image. What we'll do with this representation for rendering? We would need to receive the entire 2D imaging to be able to use an image-based rendering to be able to synthesize new views. This is one of the disadvantages of using this. We have to decode the entire image to start synthesize new views from the content. We don't have a random access in this case. We don't have a scalability in this case, but we can achieve high compression efficiency, okay? But only for images captured with planoptic cameras. If we consider camera arrays or sparser light field contents, this scheme will not lead to high compression efficiency. Okay, this is the simplest one. It's possible to achieve, but only in some cases to achieve high compression efficiency. Then we move on to another scheme, another representation that is used. That is called pseudo video sequence representation. And in this case, the idea is that since when we look at video, we have the temporal correlation. Since this temporal correlation is somehow similar to the correlation we can see when we are looking at neighboring views, we could use a 2D video codec to exploit this correlation between neighboring views. What will we need in this case? If we have the 4D light field here, the 2D array of views, we would have to scan these views in some order. In this case here, in the example, is in a spiral order. And then to stack all these views together to form a pseudo video sequence. And with this pseudo video sequence, we could use any standard to decode, to code this image, such as HVC, VVC, AV1. Since HVC, VVC can achieve high compression efficiency, we could achieve as well high compression efficiency in this case. And the only thing we have to do is to optimize the prediction structure, the pseudo-temporal prediction structure here. About rendering, what could we have in this case? Since we could have random access between this the pseudo-temporal views, we could use an image-based rendering that is incremental. As soon as we receive more views, we can improve the quality of the rendering. But of course, for having random access, we will have a trade-off between optimizing this prediction structure for random access or for coding efficiency. And this optimization may be difficult to do, okay? Another disadvantage is that since we are stacking all the views together, if we are talking about video, we will lose the temporal correlation. That's why we can only achieve high compression efficiency for images in this case. moving on to other representation, sorry, we can talk about called 4D volumetric representation. In this case, if we have the 4D multi-view representation here in the production, we can reorganize these views to be seen as a 4D volume of views. And then instead of splitting into 2D blocks to feed the codec, now we will split into 4D blocks to feed the codec. And we could use a codec that use instead a 2D transform, a 4D transform. And one example of this is the standard JPEG Plano using the transform coding mode. In this case, they use the 4D DCT and they transform this 4D block. At the rendering, we will also use an image-based rendering. And one advantage of this is that it's possible to achieve high compression efficiency for dense light fields captured with panoptic cameras. And we have in this case a royalty-free standard that's ready to be used. Okay, we don't need to pay any patents in this case, and we can code light fields with high compression efficiency for panoptic cameras. When we talk about content capture with camera arrays, the compression efficiency is not so good. And another possible drawbacks that if we want to achieve random access of views, this random access comes with the price of lower compression efficiency. Moving on to other possible representation. We have been talking a lot, but let's see, I'm almost finishing. We also have the multi-view representation. The multi-view is the production representation when we use the camera arrays and camera rigs. In this case, we have the 2D array of 2D views. And if we have multi-view, we could code this light field using a multi-view standard, such as the MV-HVC. And this multi-view standard is advantageous because it allows scalability, it allows random access, and good compression efficiency for dense light fields in general. And the only thing we need to do in this case is to optimize the interview prediction for this 2D array of views. What do we have at rendering? We could also use an image-based rendering that is incremental. As soon as we receive more views, we can improve the quality of rendering. But if we are using multi-view, we know that if we increase the number of views, or if we consider one more dimension, the temporal dimension, the code efficiency starts to decrease. And of course, if we are talking about interview prediction, if we consider sparser light fields, the coding efficiency will also decrease. Another approach trying to solve this problem, if we have more views, is the geometry-assisted representation. In this case, what is the idea? Instead of coding all the multi-view, we will select only some reference views to be coded and transmitted to the decoder side. This means that we are discarding some of the content that needs to be transmitted. And instead of sending these views, what we do? We estimate the geometry of the scene using the views. And then, for instance, we can use a depth map for each reference view to be transmitted. And then this representation could be of the kind multi-view plus depth. Other alternative is to use a graph model to represent the geometry of the scene. If we are considered the depth, we could code this representation using a 3D codec, such as the 3D HVC or the JPEG Plano for the prediction mode. Both of them use this representation based on some reference views and the depth map. The advantages of this approach in terms of coding is that it allows scalability, random access, and also for rendering, we can start rendering the views as soon as we receive the depth map, we can render more views. And a possible disadvantage is that the quality of the rendered views will depend on the quality of the estimated disparity. And when we are talking about depth map, we know that it's very challenging to estimate depth maps when we are talking about sparser light fields. And when we are talking about scenes that contain objects that are glossy or transparent, the specular objects. Another approach trying to deal with this, with specular objects, with occlusion, is the called multiplane image representation. And in this case, what do we have? We have to construct an image representation that is based on a reference viewpoint, and this reference viewpoint is seeing the 3D scene in slices. We have many slices, many places in a specific depth as we are cutting the 3D scene in slices in different planes. And then in different planes, we have all the objects that appears in this plane and the information of color of these objects and the information of the opacity, the transparency of the object. And then in this case, we can represent transparency, smoke, soft borders. We can represent more faithfully this type of objects. For each plane, we will have the texture information, RGB, and for the opacity, the transparency, we have the called alpha map. Okay, what do we need to do for rendering? If we have all these planes, the only thing we need to render an image is to blend all this plane together from back to front. And then this is called the alpha compositing. And if we want to render a different perspective, we just need to project these planes in a different direction and then blend all these planes together to render a different perspective. An advantage of this rendering is that it's very fast, okay? It's very cheap to do the rendering using this representation. Another representation is similar to the multiplane imaging, is called the multisphere imaging. But in this case, instead of using planes, we use a series of concentric spherical shells. And each spherical shells will have the color information and the alpha map. And this type of representations are used in applications with wide field of view. And this was the approach used in the last paper published by Google when they are talking about how to represent and code light fields. How can we code this type of content, multiplane images and the multisphere images? And the idea here, sorry, is to project all these planes into a 2D imaging, which is called an atlas. And we will have these projections of the color, a texture atlas, and the projection of the alpha values, an alpha atlas. And since we have two 2D images, we could use a 2D codec to code the light field, to code these 2D images. And this is the approach being considered by the MPEG immersive video standardization. One of the extended profiles is considered this. to code the MPI and the MSI representations represented by these two atlases. What can we achieve with this? We can achieve high compression efficiency if we use codecs such as HVC, VVC. But if we want to have a random access, we will have to optimize the occupancy of these atlases for both coding efficiency, random access. Then we will have a trade-off between both of them. And in terms of rendering is very fast, it's very cheap. And from the studies they are doing at the MPEG, they saw that the atlases, when they use atlases for MPI, MSI, they used to be more robust for coding errors than when they use atlases for depth, for geometry information. This was the last representation I was going to show to you. And the idea was just to show that there are many possible representations. All the representations has positives and some disadvantages, and the representation will depend on the application scenario that we are considering. Now, just to talk about very quickly, I don't know how am I about the time, but just to talk very quickly about the current trends on light field processing. And of course, if we're talking about current trends, we cannot forget deep learning. And a trend is to use deep learning all over the light field pipeline since production to the display. And I just separated some interesting works about this. And the first one is, since we have nowadays the smartphones with many cameras, all the new smartphones, every time we have one new camera, for instance, Apple has now 3 cameras and a LiDAR sensor. All of big brands on smartphones also have many cameras. The idea is it possible to generate light fields from smartphones? And there is a very interesting publication from 2018 and an extension in 2019 that tries to deal with this. And they try to, from 2 images captured from a smartphone, to synthesize other views. And how do they do that? They use the clips from YouTube where there were camera movements, and they selected many clips from YouTube with camera movements, and they produce a data set with these clips, and they use these clips to train a generative neural network, and this network builds a multiplane image representation of the scene. And this process is called inverse rendering, because now we are usually what we have the 3D model, and from the 3D model we do the rendering. Here they did the opposite. From the image they generated the 3D model. And then from this 3D model, it was possible to receive 2D images. Here the baseline was 1.4 centimeters, and then using this model, they were capable of synthesizing other views in between these two, and also synthesizing views outside the field of view of the cameras that were captured. And this they called stereo magnification. And they saw that it's possible to magnify this field of view up to 7 times using this approach. Another interesting trend is to, instead of using all the representation that we saw, to use a neuroimplicit representation of the light field. What's the idea? Is to encode all the properties of the light field that were captured into the weights of a generative neural network. And then if we have this representation, this neuroimplicit representation, we can use this representation for replacing many of the blocks in the pipeline we saw for processing: view synthesis, geometry estimation, super resolution, editing. But of course, the quality of the views that will be generated by this model will depend on the quality of the training data and also the quality of the design of the machine learning model, because we have to control using the geometry, for instance, to control what we will see at the end as rendered views. And of course, this implicit representation may be not so good, for instance, for medical imaging, where we need a very faithful representation at the end. If we compare the rendered images, has to be similar to the original one. In this case, when we are talking about guns, we cannot, we have to somehow cope with this. We don't have, we have very convincing images, but is it faithful to the input images? And this is what we can do in the future. If we can apply for geometry estimation, why not apply also for coding? And there are some papers in the literature talking about applying deep learning for coding. And in this case, the approaches are, there are two different approaches. One is to replace some components of the coding. For instance, to replace the components that does the view synthesis, or to replace a prediction inside the coding. And the other approaches is to replace all the codec by an end-to-end neural codec. And to the best of my knowledge, for light fields, most of the proposals are for replacing some components of the codec. I put here two examples. The first one is to replace a prediction inside the codec, and the second one is to do super resolution and to replace the view synthesis at the decoder side. And with this, I finish my presentation with some final remarks, just to remember from everything I was talking, that light field is used in many applications for immersive media. And one of the challenges is to deal with the huge amount of data. And we saw many possible intermediate representation for representing the light field in the processing pipeline. And the decision between them will heavily depend on the target application scenario. And of course, deep learning is expected to be used all over the entire processing pipeline, from capturing to display, in order to scale the content, as we saw in an example, and also to unlock some rendering techniques. And I finish my presentation thanking you all for listening me. And also I'd like to say that we are looking for PhD students to work on a project called LIMESA, Light Field Processing for Immersive Media Streaming Applications. We have two PhD students involved in this project. Mariam is finishing her second year, and Muhammad is arriving next week to start working with us. And we have two publications this year related to this project. This project will finish in 2024. And if you would like to live in Lisbon, I put here a picture. It's a very good place to live, sunny most of the year. Please send an email to me, and we will be happy to receive your application. Thank you.
Caroline, thank you for the very inspiring and informative talk. It was excellent. And yeah, the last part of your talk, it's really, Lisbon is a really nice place for visiting, and I believe that it's also for living. So everyone that is interested, please drop an email to Caroline. So we have some questions, and I hope I can also make my own questions at the very end. The first question came from Professor Ferrugem. He says that he's working with myself and also with Professor Agostini on the use of light field sensor for calculating distance and recognizing objects in the scene. The question actually is, how do you see the use of light field in autonomous cars and robots in general?
Okay, I focused the presentation on entertainment, and I didn't talk about computer vision using light fields, but of course we could apply these technologies, and there are many. One of the people working on this is Donald Danseron. He has many works on how to capture the light fields and how to use light field cameras to measure the distance between the objects I think we could use also light field systems, many cameras capturing for rendering light fields in a robotic system. I don't see, but I don't know if I answer. I don't know what exactly, how do I see the use of light field? I think it's in capturing the data and also processing this data for measuring the distances and using this type of stuff. I don't know if I answered the question.
Yeah, I believe so. Thank you. Then Professor Mateus will ask his question, but before moving to this question, I just want to let you know that there are many comments thanking for the nice presentation. I see also one of your PhDs is sending you a message here. That's thank you for the nice presentation. Guilherme is asking you to send some pastéis de nata from
okay.
That will be also, I'll take some if you can make it.
Okay.
So, and then I go back to Professor Mateus' question. Professor Mateus, I think you want to ask by yourself, right?
Hello, yes, just to make things a little bit more dynamic. Thank you, Caroline, very, very nice presentation. Actually, my question was stolen from Guilherme, but I have another one. Actually, I had several questions, but since your presentation was so wide and you covered everything pretty much, I was just like, okay, crossing them out. Yes, you already answered this and this. Very nice, congratulations. My last question that remained was, in terms of data sets, what can you recommend for people who want to start working in this field, especially using deep learning or any machine learning algorithms and techniques? I see that there are a lot of efforts to increase the number of light field information using machine learning itself, perhaps. Can you recommend any open data sets for people who want to start studying this area?
Yes, data sets is the huge problem when we are talking about deep learning with light fields. It's really difficult to find good data sets. Now I don't have the references, but there is a page on the internet. I think I don't remember exactly the page where they used to put all the data sets that are available. But I think for deep learning, it's very difficult. It's very difficult to find. And I think an approach that can be used is this one, using clips of camera motion for training the deep learning. And they have a data set. I can provide afterwards the links for these data sets of camera clips. Okay. But it's very, very difficult. This is the problem. That's why we are struggling now to work on light fields with deep learning, because it's very difficult to find data sets. And maybe this is an interesting work to do, to produce data sets for deep learning using light fields.
Yeah, just to connect, we had this question from Professor Ferrugem earlier, and actually we are using deep learning for depth inference, and we are also building some data set at home, let's put like this, because it's really challenging. And of course, if you want to infer the depth, you don't really want to use Blender sort of stuff. You really want to have those intrinsic specifics from the camera, right?
Yes,
so
yes. we are also working on segmentation, and it's very difficult because with segmentation, we need the images, but we need also the labels to train if we are going to use supervised learning. And it's impossible to find data sets of this kind. And some ideas for you that is starting working. Let's produce data sets.
Yeah, it is.
And now I'm going to use for sure.
Oh yeah, we can share this effort, right?
Yeah.
Then I move to the question from Professor Guilherme. That's actually the second question from Mateus, and I think this is a really tough one because this is really wide. So, Professor Guilherme, thank you for the talk.
I'll be able to answer.
Yeah, but I think you can like use maybe another 3 or 4 hours to answer this one. Among the light field representations you presented and the encoders we have nowadays, what would be the best option if you want to minimize coding, decoding / rendering complexity? So what? Bring us the complete solution now.
I really want to know. I really want to know this, but I think it's too tough to have one solution for all the problems. I think at this moment, we will have to focus in some of the problems, because if we want high efficiency coding, we can use HVC, but HVC is very complex. Any other coding that uses, is based on the HVC will be complex. And maybe a solution that can decrease a little the complexity on coding the code would be the one using geometry information. But then the complexity goes to the rendering. I don't know. We will always have to deal with this.
Yeah, the trade-off's always there, right?
Yeah.
Then just to point out that Marian Hamad, that one of your PhD students, I think she just shared with all the audience the link for some of the data sets. So please go there. I think this will help you in this sense. Just to point also, Caroline, that we have nearly 80 people attending us right now, and I just went through and we have many people that were speaking at the previous edition. I've seen Carla, I've seen Fernando, I've seen Carlos Cosme. So this is really nice that we have this moment to bring everyone together and discuss those visual signal processing problems, right? If you allow, I have one question. I prepared some, but I'm not sure which one I prefer. I think I'm going to this, trying to understand how those immersive applications are going to be in the future. So we see your talk, of course, was concentrating on light fields, but we have seen a lot of effort on point clouds. We know that we have all these techniques to translate between those representations. What do you see, or how do you see the future in terms of those technologies? Like, which one will be more widely used? Do you think they will be more like niche or more for broader use? How do you see that?
In my opinion, I like to see what the industry are putting money on, then we can have some ideas what is the path. And I think big companies like Google and Facebook are investing on VR, mixed reality. And I think they will try to convince us that the future is VR and AR applications, and somehow they will put some appealing application for us, and we will start using without we will start needing that as we need now social media. I think this is the future, the mixed reality.
And then in this sense, both or even other sort of data representations will be there.
Yes, I think I like to think that light field is good for capturing, and then we have many representations. That's why I did a different, because sometimes they talk about there is only two options, light fields or point clouds. I think light fields important for capturing, and for representing, we will have many representation. That's why I think in a system that is somehow agnostic, that any representation will be possible, will be the future.
That's really interesting. And I don't believe we have more questions. I will conclude with one from my side. We have seen, you mentioned standards, efforts in terms of new standards for immersive data. And we see there's a lot of things happening both at JPEG and MPEG-I. And I want your impression in the sense that, especially in terms of MPEG-I, we have seen that a lot of effort trying to use technology, let's say, create atlases or modifying the representation and use off-the-shelf, let's put like these video encoders. Do you think this is really the solution that we need, or this is a solution for the coming years? Why?
Sorry, I don't know if it's only me, but I stopped listening, Bruno.
No, I think his connection got cut for some reason.
Okay. I will stop the sharing. Let's see if it will.
Yeah, I think we lost Bruno for now.
Okay,
I'm not sure if he's coming back, Caroline. So I'm not sure if
we can talk.
Yeah, I'm not sure if you got the question or not. I think he couldn't finish, right? So
yes.
Maybe we can try a few seconds, but if he doesn't come back, I just want to say once again, thank you very much for joining us. We definitely want to visit you. Yes, we definitely want to visit you at Lisbon and welcome you here in Brazil whenever you want to, as soon as this pandemic leaves the world, hopefully soon. And it was a very interesting talk in a very a hot field in the area. So we hope our students are as inspired as we are by your presentation. Thank you very much.
Thank you very much. And I hope to see you all personally very soon.
Definitely. Lisbon is such a very wonderful city. I hope everyone gets the opportunity to visit once in their lifetime. Thank you.
Yes, again, we are looking for PhD students. Please get in touch with us.
If you want to, you can leave your email on the chat, so then people can contact you if they're interested.
Okay. Thank you, Mateus.
Thank you, Caroline.